All right, so now let's talk about hydration reactions. Let's just pick apart this word real quick. Of course, we've heard hydration with regard to drinking more water and all that good stuff. And that's exactly what these types of reactions are. They're going to be the addition of H2O, or more specifically, hydrogen will be added to one of those vinyl positions and OH will be added to the other one. Okay, so you can see that combined, those are a water molecule that's going to be added to these double bonds. So we're going to learn about two different types here. The simplest is just this acid catalyzed hydration. So just like before, so first let's just look at the product real quick. Again, what we're going to see is that we have an OH added to one of our vinyl carbons. That would be this guy here. And then on the other side, what's being added is that implied hydrogen is being added to the other side of my double bond. Okay. Again, these are acid catalyzed. So simplest way that you're going to see these drawn is with the addition of the hydronium ion. More specifically, what's actually used in the lab is usually a strong acid catalyst. So for example, sulfuric acid in the presence of water would give you these hydrations. We're going to look at the mechanism, but we will see that these are Markovnikov regioselectivity, which means that that OH group is going to be added to the more highly substituted carbon. And let's take a look at a few examples of different alkenes. So notice that the difference between these alkenes is how highly substituted one of those carbons is. And notice that my reaction rate increases dramatically depending on how highly substituted that carbon is. So this is again consistent with this idea of a carbocation intermediate in our reaction mechanism. So very similar to what we saw with our strong acid, HBr, HCl, HI, hydroiodic. The first step in these reaction mechanisms is our double bond is playing the role of a base. So that means our double bond is going to reach out and grab that acidic proton. Okay, that would kick off whatever is on the other side of that acid. In this case, it's a water molecule. And most importantly, that would leave us with a carbocation. And again, these are going to be Markovnikov because the carbocation wants to form on that more highly substituted intermediate. The next step is again nucleophilic attack, but this time our nucleophile isn't a halide ion, it's actually just water. So water will become our nucleophile and come and attack that electrophilic carbocation. Now we're not done yet because once water attacks, it joins, right, as H2O, meaning it has that positive charge. This is what's called an oxonium ion. And so the last step is going to be the deprotonation of that oxonium ion, leaving us with just our alcohol group. Okay, so this is the Markovnikov addition of an alcohol group to your alkene. In terms of reaction conditions, we actually want to use, if we want this to proceed towards that alcohol product, towards that addition product, we're going to want to use dilute sulfuric acid. And that's because by using dilute sulfuric acid, it would have a higher concentration of water in there, right? So since water is one of our reactants, increasing the concentration of water just by Le Chatelier's principle will push the reaction towards that product side. One of the things we've talked about a little bit, but haven't really gone into detail too much, we will when we talk about alcohols, is that sulfuric acid, or strong acid in the presence of an alcohol, can actually protonate that alcohol, making it a really good leaving group, right? So by having concentrated sulfuric acid, which has a smaller concentration of water, we can push that reaction back towards the elimination product. So just in terms of reaction conditions, we actually want to use dilute sulfuric acid. Okay, so let's look at this here. Here's my alkene. I'm going to indicate or locate my vinyl carbons. And now I'm going to ask myself, which is going to get my alcohol group. Cat's going crazy outside. Again, in this case, let me actually choose different colors. In this case, my alcohol group, again, these are Markovnikov additions. So my alcohol group is going to go on the more highly substituted carbon. In this case, it'll be that green carbon. But again, now we're going to think about stereochemistry. What do we know about those carbocation intermediates? Well, they're not stereoselective. So in terms of our products, we would get a mixture of the R and the S enantiomer. Again, both of these have addition to that more highly substituted carbons, but in one, the OH group came from one side and the other, it came from the other side. So we get this racemic mixture of our R and S products, right? So these are not stereoselective. Okay, now we're going to talk about a very similar reaction in terms of the products that we obtain, but it's got a different mechanism. And this is oxymercuration, demercuration. Okay, so these are going to use this reactant right here. It also gives the Markovnikov product. Okay, so starting out with this alkene, this simple alkene, we still get that Markovnikov product where substitution of that alcohol group is on the more highly substituted carbon. So then what's the difference? Well, there's a few. One of the things that we're going to see is because it doesn't go through a carbocation intermediate, there's no rearrangement that occurs. Another important aspect of these oxymercuration additions are the stereoselectivity. Okay, so this is our first example of a reaction that's stereoselective. So let's see how that works. The intermediate here, how these reactions go, and you don't have to memorize the reaction mechanism for this one, but it helps to explain why it's regioselective. So let's just see what I mean by that. Is it actually goes through this cyclic mercurium ion intermediate. Okay, so just like before, we have our double bond playing the role of, in this case, a nucleophile. It's going to reach out and grab that electrophilic. In this case, it's this weird mercury complex. And that temporarily creates a carbocation, but what happens is the mercury goes and interacts with that carbocation immediately to form this cyclic intermediate here. Okay, so what happens then? We've formed our cyclic intermediate, and now the nucleophile, the other nucleophile, in this case water, is going to go and attack, but it can only approach from one side. So there's two possibilities here. What we would call a syn addition, meaning it's going to approach from the same side where that mercury is, syn, same side, or the anti-addition, meaning it's going to approach from the other side. Only one of these occurs. Which do you think it is? So it's this anti-addition here. You don't have any syn addition because it's blocked up by the presence of that cyclic intermediate. So these are stereoselective in that you only get the anti-addition. The nucleophile and the hydrogen that are being added are going to be added to opposite sides. Okay, so just to illustrate that here, what we would have, for example, in the other product, you don't get a stereoisomer that's formed, so it's not as interesting, but let's look at this example here. Here we have these two vinyl carbons. One of them is going to get the OH group, one of them is going to get the hydrogen, but importantly, those are going to come from opposite sides, right? So here, the OH group that's being added and the hydrogen that's added, notice that they are on opposite sides. One of them is pointing into the board, one of them is pointing out of the board. And you'll also get the enantiomer, but again, importantly, those two additions are happening to opposite sides of the ring. Okay, so you're not getting all four possible stereoisomers that you would expect if, for example, you did an acid-catalyzed hydration. You're only getting two of the four stereoisomers, both having these stereoselectivity because of that anti-addition. I guess just to point out here, this last step, this sodium borohydride, what that's doing is replacing that mercury with a hydrogen, right? So the water will attack on one side, and then the mercury is going to be replaced with a hydrogen on the other side. Okay, but these are, importantly, these are anti-additions. This is a stereoselective reaction. Okay, so then lastly is this idea of rearrangements that may take place between the two reaction types. So up top here, we have hydration, acid catalyzed. And this will proceed through a carbocation intermediate, which means that we always have to be on the lookout for rearrangements. Right? If there's a more highly substituted carbon as your next door neighbor, you can have a hydride shift or a methyl shift in order to form that more stable carbocation. With the oxymercuration, demercuration reaction pathway, there isn't any intermediate that, or any rearrangement that can occur because you don't go through a carbocation intermediate. You go through that weird cyclic mercurium ion intermediate. So these will not rearrange, even if there is that next door neighbor, more highly substituted carbon. Okay, so something that you got to be on the watch for these two different paths. The other last thing to be said with regard to the oxymercuration demercuration is it actually works with any nucleophile, not just, so we've been doing H2O, which would then lead to an alcohol group on that more highly substituted carbon. You can do this with any weak nucleophile. So for example, you could have ethanol as well. And so what that would do would mean that ethanol is going to behave as my nucleophile. And at the end, I would get an ether. Right, so where that oxygen is again behaving like a nucleophile, but it's not going to then turn into an alcohol group. It's going to be an ether group. Another way, I guess, just to, oh, bummer. Draw out the whole bonds or the whole bond line structure. Right. So using these, this oxymercuration, demercuration, but doing it in the presence of ethanol or methanol as opposed to water, you would get an ether as opposed to an alcohol. Okay, so just to summarize here again, both of these give you the Markovnikov product, the more highly substituted product. One of the big differences is just whether or not you get the rearrangement product. So in the presence of the acid catalyzed hydration, your major product would be this rearrangement product where the carbocation is formed on that more highly substituted carbon. Whereas if you use the oxymercuration demercuration, the only product you're going to get is the non-rearrangement, right? Rearrangements aren't possible in oxymercuration demercuration. Okay, so again, just to summarize, get a little cheat sheet going here. For acid catalyzed hydration, you do have to know the mechanism for that. And again, that goes through that carbocation intermediate. For the oxymercuration demercuration mechanism, you do not have to know the mechanism for that other than to know it has that, whoops, cyclic intermediate. For the regioselectivity of the acid catalyzed hydration, this is Markovnikov. And watch out for rearrangements. for the oxymercuration, demercuration, these are also Markovnikov, but there are no rearrangements. All right, and then lastly, stereoselectivity. Acid-catalyzed hydration is not stereoselective, right? It goes through those carbon-cation intermediates. For the oxymercuration, demercuration, these are stereoselective, and in particular, you will only see the anti-addition. Okay, so this is our first example of a stereoselective type of addition reaction, and these are anti, meaning both groups are going to be added from opposite sides of that double bond. We'll see examples of syn addition where they're both from the same side, anti-addition, they're coming from opposite sides.